Okay, let's unpack this. So, up until now, the programs we've talked about have been, well, incredibly obedient.
Right.
They just execute in a straight line, top to bottom. The only time they really divert is for a quick function call.
It's like a recipe. Step one, then step two, then step three. Very rigid.
Exactly, like a grocery list.
Yeah.
But, I mean, a truly useful program has to be smarter than that. It needs to be able to adapt.
But that linear execution just limits a program so severely. I
Hmm?
mean, think about it. If a computer needs to react differently based on what a user gives it,
Yeah.
maybe approve a $50 purchase, but flag a $5,000 one.
It can't follow the same set of steps for both. It has to make a choice.
It'd have to make a decision
Yeah.
and then execute the right path based on that decision.
So we're moving beyond simple obedience here and into genuine digital decision making. It's not that different from how we make choices, is it? Should I go to college? Do I need a coat today? It's all based on conditions.
And that is the absolute core of this deep dive. Conditional execution. These are the tools that let the computer look at data, compare it, and then decide which chunk of code to run and which to just skip entirely.
We're basically giving the program a brain.
A digital nervous system. That's a good way to put it.
So our mission today is to really decode the mechanics of this system. We'll go from the simplest check, is this number bigger than that one, all the way to complex layered logic that turns static code into something powerful and adaptive.
All right, let's start at the very, very beginning. Before a computer can decide what to do, it has to figure out if a condition has been met. How does it actually measure two pieces of data against each other?
That's where comparison operators come in. They're literally the tools we use to ask the computer a question.
A question with only two possible answers.
Exactly. They're called binary operators because they take two things, an operand on the left and one on the right, and they compare them. The result is always one of two things. And we use a standard set of symbols for this. I think the first one, the most important one to get right, is checking for equality.
Right. We use the double equal sign, GATGeopols, to ask is x equal to y? And it is so important to understand why it's a double equals.
Oh, this is the classic trap.
It's the classic trap. If you accidentally use a single equal sign, which is for assignment.
You're not comparing anything. You're just changing the value of x to be the same as y.
Exactly. You're assigning, not comparing. And your program will probably still compile, but it will behave completely wrong, and you'll be pulling your hair out trying to find the bug.
A silent killer.
It absolutely is. So beyond equality, we have AV. For inequality, is x not equal to y?
And then the standard ones for size.
Right.
For greater than, for less than.
And of course, the inclusive ones for greater than or equal to, and error for less than or equal to.
Yeah.
That really covers all the bases for comparing numbers.
So no matter what you're comparing, two integers, two decimal values, the result is always what?
It's always a Boolean value. That's the key. The answer to the comparison is either true or it's false. And the source reminds us, technically, that's often just a 1 for true and a 0 for false under the hood. That simple 1 or 0 is the key that unlocks the next piece of code.
Okay, so once we have that crucial true or false, we need the actual structures to, direct the traffic. You mentioned there are three main ways programmers do this.
That's right. The first and simplest is the one-way selector. You'll know this is the basic if statement.
So this is the one that says, hey, if this one thing is true, run this special block of code. If it's not true, just move on.
Precisely. If the condition is false, the computer literally just jumps over that entire if block and continues on its way. It's for adding optional behavior.
Then we level up to the two-way selector, the if-else statement. This feels different. It feels less optional.
It is. Think of it as a fork in the road. You must go left or you must go right. There's no other option.
So if the condition is true, the if part runs.
And if the condition is false, the program is guaranteed to run the else part instead. It's one or the other. They're mutually exclusive.
And then this is where it gets really interesting. The multi-way selector, which is where we chain conditions together with else. If the two-way selector is a true-false question, this one is like a multiple choice test.
Exactly. A multiple choice test where only one answer can be correct. This is essential for things like, say, converting a numeric grade into a letter grade. Is it an A, a B, a C, a D, or an F?
And with that example, I think the flow of how the computer checks things becomes absolutely critical.
It's everything. This is where programmers can get into a lot of trouble.
Because the computer checks strictly from top to bottom, right?
Strictly. It starts with the first if. If that's true, it runs that code block. And then, and this is the important part, it skips the rest of the entire chain. It doesn't even look at the other else if conditions.
So the order you write them in matters immensely.
It's the key to making it work correctly. Let's go back to that grading example. Say you check for a B, which is a grade over 80, before you check for an A grade over 90.
Ah, I see the problem. A student with a 95.
A 95 is greater than 80, so it would match the B condition first.
And it would stop right there. It would never even check for the A.
Exactly. The student gets a B, and the logic is wrong. You have to check for the strictest condition first. Check for the A, then the B, then the C, and that final else at the very end.
That's the catch-all.
That's the catch-alls. If nothing else was true, that's what runs. In this case, it's the F. It guarantees one and only one path is taken.
Okay, so we can handle individual conditions, but real-world logic is almost never that simple, right? A single comparison often isn't enough.
Very rarely.
A program might need to check 2 or 3 things at once, like you're eligible for a scholarship if your GPA is over 3.5 NE, you're a full-time student, 2 conditions.
And that's where logical operators come into play. They take all those individual true-false results from your comparisons and combine them into one final single Boolean value.
The decider.
The decider. And in C++ Q, we really rely on 3 main ones: Adderas and Delay.
Let's start with NAE, the AND operator. This one feels like the strictest one.
It is. It's a gatekeeper. If you have condition 1A and D, condition 2, they both have to be true for the whole thing to be true. If even one of them is false, the result is false.
Like needing a passport A and D, a boarding pass, you're not getting on the plane with just one.
Perfect analogy.
Yeah.
Then you have a row, the OR operator. This one's much more forgiving.
Safety net.
Exactly.
Yeah.
With OR, if condition 1 is true or condition 2 is true, the whole thing is true. It only becomes false if both of them are false.
And the last one's a bit different. Oh, the not operator.
Yeah, this one's a unary operator. It only takes one operand, and all it does is flip the result. So if something was true, not makes it false, and vice versa.
People often use that to check if something is not true, right? Like if R and came cis.
It's very common for that. Now, if you start combining all 3 of these in one big, complex expression, there's a strict order the computer follows to figure out the answer. It's called precedence.
Which is super important because if you get the order wrong in your head, the logic won't work the way you expect. So what's the hierarchy?
It's non-negotiable. Not T, the operator, is always evaluated first. It has the highest priority.
Okay.
Then comes A and D and a D. And finally, last in line is OR, R. So it's not T, and A and D, then OR. Knowing that is essential to translating complex rules into working code.
And just to touch on it, if you need even more complexity, you can nest these things, right? An if statement inside another if statement.
You go as deep as you need to.
Yeah.
But before we move on, there is a really neat shortcut in C++ for simple two-way decisions.
You're talking about the ternary conditional operator?
I am. It's called ternary because it takes 3 operands.
And the syntax looks a little wild at first. It's like condition dot expression 1 dot expression 2.
It does look strange, but it's just a compact one-line if-else. If the condition is true, the whole thing evaluates to expression 1. If it's false, it evaluates to expression 2.
So it's perfect for a simple assignment.
Perfect. Like, is the user an adult? Yes, the label is adult, otherwise the label is minor. It's much cleaner than writing out a whole if-else block for something that small.
All right, moving on to some more specialized tools. For certain situations, there's an alternative to that long else if chain we talked about, the switch statement.
Right, the switch statement is fantastic when you need to test one single variable for equality against a list of very specific values.
So each of those possible values is called a case.
Exactly. It can be a lot cleaner to read than a long chain of ifs, but it has a very important limitation.
And that is?
It only works on integral type variables.
Meaning whole numbers, so integers, longs.
And even characters char, because they're just numbers underneath. But you can't, for example, use a switch statement with floating point numbers or with strings of text.
The source material mentioned a really great real-world use case for this. Building a menu for a command line interface, or CLI.
Yes. Think of those old-school airline check-in screens, or even the point-of-sale terminals you still see at places like Home Depot. Press 1 for new sale, 2 for return, 3 for lookup. That's a perfect job for a switch.
And that example brings us to what you said is the most critical detail, the thing that causes the most bugs with switch.
The break. Or, more specifically, the lack of an automatic break.
So what happens if the program finds a matching case, say the user pressed 1, it doesn't just stop there.
It doesn't. It will execute the code for case 1,
Yeah.
and then it'll just continue on and execute the code for case 2, and then case 3. It's called falling through.
It just keeps going until it hits a break statement.
Until it hits a break or it reaches the very end of the switch block. So you must manually put a break at the end of each case to tell it, okay, we're done here, exit the switch. Otherwise, your new sale option might accidentally run the return code right after it.
Okay, that's a huge thing to remember. Finally, let's talk about getting input. Usually we prompt the user, but there's a more direct way, right? Passing arguments to main.
Yes, the main function itself of the program's entry point can take arguments directly from the terminal when you run the program.
Which is way more efficient than having the program start up and then sit there waiting for you to type something.
Much more. And this ties directly back to our topic of conditional logic,
How so?
because the very first thing your program should do is a conditional check. If you expect the user to provide, say, an input file name and an output file name,
Your first if statement should be, did I receive exactly 2 arguments?
exactly. If they only gave one, or they gave three, your else block should print a here's how to use me message, and then just exit.
So technically, how does that work? You just type them after the program name.
Yep, separated by spaces. And if an argument has a space in it, you just wrap it in double quotes. The only catch is that they all come in as C strings as text. So if you need a number, you have to write code to explicitly convert it.
Yeah.
So that really completes our deep dive into conditional execution. We've seen how these comparison operators, they generate those fundamental true-false results.
And that one capability moves a program beyond that simple linear path. It gives it a kind of intelligence.
Adaptability, for sure. And we saw how we handled those outcomes using the three main structures. The simple one-way if.
The two-way if-else for choosing between alternatives.
And a really useful but sometimes tricky multi-way else-if chain, where we learn just how vital the order of your checks really is.
We also build up to more complex decisions using logical operators, the AND or R and not one, and even looked at that compact ternary shortcut.
And all these tools allow our programs to make these sophisticated choices, whether it's, figuring out if you're eligible to vote or calculating a personalized result based on your input.
If you want a final thought on just how much complexity can be built from this simple logic, think about creating an AI for a game like tic-tac-toe.
Oh, that's a great example.
It seems so simple, but to make the computer play intelligently, you have to check for every single possible winning condition.
The 3 rows, the 3 columns, the 2 diagonals.
For both players, on every single turn. That decision-making structure translates directly into dozens of nested and layered conditional statements. All of that game-winning strategy flows from the most basic operation we discussed today, just asking if 2 little x's or o's are in the same place. That is the power of conditional execution.